Hi, my name is Jonathan Mugen, and this is work that I've done with my advisor, Ben Kuipers. So the world is a chaotic place. There's a huge amount of sensory input that comes in, and we like to be able to make sense of it and ultimately predict it and control it. One thing we can do is we can track objects. Tracking objects allows us to boil this huge sensory input down into a set of objects and relationships between them. And so we could have the locations of objects and the location of one object relative to another object. And the result of this is a set of continuous variables. And so we get a representation that looks like this. We have a set of variables that changes values over time. The blue lines represent the values of variables such as the locations of objects and the distances between them, and the red is their derivative. So what we see here is that this system is still very chaotic, and we'd like an algorithm that can learn to control it and predict it. And the rest of this video will explain how we attack this problem. So the environment that we work in is a simulated one with a robot. It has a hand, a block, and two floating heads. Initially, the robot knows nothing about the system. It looks just like what we just saw. But through working with it, the agent should learn models about it and ultimately how to control it. And the way we do that is a method we call QLAP. So QLAP begins with a set of continuous variables that come in. From these continuous variables, QLAP discretizes them. From these discretizations, QLAP can make models, and then from the models, QLAP can find new discretizations. The models then are converted into plans. The plans are different ways to perform actions, and then the agent can put these all together into a plan and action network that represents its knowledge. So QLAP uses a qualitative representation. Here we see a variable x on a number line. When we add two landmarks, we can divide that number line into 5 qualitative values. And then a variable is at one of the 5 qualitative values, and it can also be moving in a particular direction. These landmarks that QLAP learns allows us to define events. And from events, we can start to look for contingencies. Contingencies of the form if A happens, then B will soon happen. And here we see the different colorings represent the probabilities of various possible contingencies. Here we found one. We can convert it to a model where A leads to B. And then when we have that model, we can then start to add context variables to make it more reliable, and then we can track statistics. The models also allow us learning landmarks. For an event A, we can look to see if event B follows, and then for some variable, we can look at its real values and see if there's a cut point that better predicts when B will occur. Okay, so we have a pairwise search for contingencies. When one is found, it's extracted, and then we add context variables and make it more reliable, and then we add new landmarks, and this goes around and around, making more models and landmarks. The landmarks allow us to represent the world qualitatively. Here we see the same time series that we saw previously, except now it's a qualitative representation, and the red is the current value of each variable at each time step. And then as the agent learns more landmarks, it gets a finer representation of the world. And so once we have these models, we can convert them to plans, the plans to actions, and it's hierarchical because actions call other actions in QLAP. And here we see a representation of the agent's knowledge, and we see how the knowledge changes as it explores. Roughly speaking, you could say that it's the agent's brain, and so as the agent explores, it learns more plans and actions. And these plans and actions allow it to do more things. Okay, so we have our agent in the environment. It receives a flood of information coming in the form of continuous variables, and we want it to learn in a completely unsupervised fashion. So it starts off by motor babbling. But as it learns more about the environment, it builds models, actions, and plans. And then once it has these actions, it can use them to explore the environment actively by picking actions to explore. But then after developmental learning, we can give the agent a task. For example, we can tell it to hit the block in a particular direction, either left, right, or forward. And it's fun to watch that sometimes it doesn't do very well. Like in this case, it's having a little trouble. It's trying to hit it forward, but doesn't quite get it. But then eventually it does. Because it's pretty flexible the way it learns, because it learns multiple plans for each action. And so if one doesn't work, it can try another one. Another evaluation we can have is we can have the agent try to pick up the block, which in this case means center the bottom of its hand over the top of the block. And what's interesting is it has to know what centering means, because initially it just has this long set of continuous variables, and it has to find the right discretization, and it does that through the model building process. And to achieve all this, the agent has to learn to make a long sequence of decisions, all at the right time, all in a continuous environment. That's the end. Thank you.